Good day and welcome back for our fourth and final installments on limits and continuity. And truly in this video, it's going to be on continuity. In the previous three videos, we introduced the idea of limits, explored their properties, saw examples where the limit does not exist, and examples where the limit does exist. To continue working towards the idea of differentiation, it's worth pausing and discussing in this video what it means for a function of two variables to be continuous. And we begin with a reminder from Calculus 1, something that we kind of foreshadowed a bit in a previous video. So from Calculus 1, we would say that a function f of x is continuous at a value x equals a if and only if the limit as x approaches a of f of x is equal to f of a. And remember the thing I mentioned on a previous video is that it's essentially telling you that a limit of a continuous function is the easiest possible limit for us to evaluate. We simply take that value a and we substitute it in for x. And as we typically do, to extend to a function of two variables, we do the thing that makes the most intuitive sense. So a function of two variables is continuous at an ordered pair a comma b if the limit as xy approaches ab of the function is f of ab. So once again, it's going back to this idea that in order to evaluate the limit of a continuous function, you simply substitute those in. And we could take this a bit further, and we say that a function is continuous on some set D. So this would be a bunch of ordered pairs in the xy plane. So D is in the xy plane, and we're continuous on this set D if F is continuous at every point in D. So at every, let's say, a comma b in that set D. And the big observation I want to make, and the most important point I want to get across for this topic, is that all of the basic functions we encounter are continuous wherever they are defined. That is, all of these basic functions that we encounter on a regular basis, think polynomials, powers of x's and y's, constants, trig functions, exponentials, natural logs, inverse trig functions. All of these things are continuous as long as you stay in their domain, where it makes sense to talk about them. So we have to be careful of things like dividing by zero, taking square roots of negative numbers, and those basic built-in domains to things like natural logs, trig functions, etc. So maybe to start off with, I've said the word polynomial. What is a polynomial of two variables? And because polynomials and rational functions are things that I will reference occasionally moving forward, it's important to make sure that we're all kind of on the same page. What is it that I mean when I refer to a polynomial of two variables? And a polynomial of two variables is very simply put going to be a sum of terms, i.e. adding up, of the form here, where c is a constant, you have x to a positive whole number, y to a positive whole number. So for example, just to kind of illustrate this, maybe you have something like f of x comma y, a function of two variables. So 2x squared y squared plus 3xy plus y to the 7th minus 101. This would be a perfectly good example of a polynomial in two variables. Note each term takes on this generic form. A constant times x to a non-negative whole number power, y to a non-negative whole number power. And a rational function is a quotient of two polynomials. That is a polynomial divided by a polynomial. So for a rational function, let's call it r, it might be something like x squared y squared plus x minus 1 over x cubed plus y cubed plus 2. A polynomial divided by a polynomial. And polynomials and rational functions are nice to work with in the sense of continuity. So polynomials are continuous, I'm just going to say everywhere. And by everywhere, we mean everywhere they are defined, and a polynomial of two variables could be defined for every single input in R2, that is the xy plane. Similarly, rational functions, they are not continuous everywhere, they are continuous everywhere they are defined. That is where we're not dividing by 0. So rational functions are continuous on their domain. And with this observation in mind, I want to go through two additional examples. One illustrating kind of how quick and efficient certain limits can be with the above observation, and then another finding kind of a region where a function is continuous. Both of them kind of common problems that we encounter. So with this limit, I want to note that we have a limit of a polynomial in two variables, and we said polynomials are continuous everywhere. So specifically, it must be continuous at this point 1, 3. And if it is continuous at 1, 3, we simply take that point and we substitute it in to the function. So the value of this limit, and let's do kind of an intermediate step. If we're thinking of this as being the function f of xy, we simply replace each and every x with a 1 and each and every y with a 3, which you could do directly, but I want to make the correspondence back to that definition of continuity as clear as possible. So this becomes 4 times 1 squared times 3 plus 3 times 1 times 3 squared, which is 12 plus 27, which is 39. And I think you would all agree with me that this observation of continuity really makes the limit quite a bit more efficient for us to evaluate. The other common type of problem we might encounter dealing with continuity would be for a function such as the one given here. What are the inputs, the pairs of the form x comma y, where this function is continuous? And similar to calculus 1 and 2, if the top and the bottom are continuous, then the quotient will be continuous wherever you're not dividing by 0. So remember, you do not need to overthink this. Let's work through some details. So the sine of xy, this is continuous everywhere. So there's no restrictions in terms of what we can plug into the sine of xy. The reason being is xy is a polynomial which is continuous, and sine is a trig function which is continuous everywhere. So their composition would be continuous wherever it makes sense to talk about them. Similarly, e to the x is continuous, y squared is continuous. So e to the x minus y squared is continuous everywhere. So the only other thing that we need to worry about is combining these two quantities together. So f of xy is continuous whenever the denominator is not 0. So once again, we're just staying inside that associated domain. So whenever e to the x minus y squared is not 0, which is equivalent to saying y squared is not e to the x, or y is not equal to plus or minus the square root of e to the x, which we could write as plus or minus e to the 1/2 x. So our conclusion then is the function f of xy is continuous whenever y is not equal to e to the x over 2. So that completes our discussion of limits and continuity. And as usual, I'd just like to note that there are plenty of really good suggested problems in the book to go over. And remember, as you're going over those or working through these videos and notes, if you have questions, do not hesitate to contact me. Drop me an email or stop by the virtual office hours. In our next topic, we will begin differentiating functions of two variables. So stay tuned and take care.